Okay, so in this video we are going to be covering note 3 from CS70, and the whole purpose of this note is to introduce us to induction. So what does induction tell us? It's basically tells us that something holds over the set of all natural numbers, right? That's sort of the goal. That's its purpose. Now there's a specific process we use to implement induction, and it's very formulaic, and you sort of end up getting a decent amount of points on tests if you're just able to recall these steps and sort of fill in the theorem or claim you're trying to prove according to those steps, right? So let's just get into what those steps are. Alright, so we have these 3 steps here. We have a base case, which must show that our statement holds for some initial value. Typically it's 0, because again, we're trying to show something holds over the set of natural numbers. Then we have to formulate an induction hypothesis, which will say, in this type of induction, that our theorem holds, or our proposition, I should say, holds for some value that is greater than or equal to our initial value, right? And the inductive step says, well, if that's true, if P of k is true, then we want to show that P of k plus 1 is also true. That's the step, right? We're trying to show that the next step is true. And the metaphor they like to use in the notes is that if it's true for one value, then it must be true for the next, then it must be true for the next, and it sort of creates like this domino effect, right? And so we're going to sort of illustrate how this proof works by looking at the different theorems, and we are going to switch over to Paint to look at theorem 3.1. And theorem 3.1 states that, and let me actually just write it out really quick. Alright, so this is the proposition that we were trying to prove. We were basically saying for all numbers in the set of natural numbers, the sum of all numbers leading up to our number is equal to our number times our number plus 1 divided by 2, right? And we're going to represent this entire proposition, I guess really, like honestly, this whole thing, as P, right? And simply following our set of instructions from the Processes tab above, the first thing that we want to do is implement our base case. So I'll just call it BC. And essentially we want to prove that the statement holds for the smallest value given our set of values, right? So, the smallest value could be 0, right? So let's say n is 0. If we plug in 0 into here, so this value right here, we're going to see, n is equal to 0. We're going to see 0 times 0 plus 1 over 2 is also equal to 0. So the sum of all the digits from 0 to 0 is 0, which is also represented by, this formula right here. So that basically proves that our base case holds. The next thing we want to do is formalize our inductive hypothesis. And what that's basically going to say is we're going to say, let there be some arbitrary k that is greater than or equal to 0, such that P of k holds. So we're going to say P of k is true. We're just going to leave it as that, and we're going to say for as long as k is greater than or equal to 0, right? Okay. And now we have to take our step, and the way that we handle proving our step is by, in this case, doing some sort of algebraic manipulation to get things to look like each other, right? And that's sort of the basic premises. We're going to have our induction hypothesis, and we're going to want to make it look like our induction step. And so I'm going to say let n equal k plus 1, and we're going to say we want to show P of n, right? Okay, so how are we going to do this? I am going to scroll down a bit just so we can get more room. And I guess the first thing I'm going to do is really quick, I'm going to rewrite our formula, and then I'm going to, if you remember, actually, I'm not going to rewrite it. Let's just remember what we have up here. Originally we have n, and then we have n here, right? But really what we want to check for is k plus 1 in this case. So we're essentially going to substitute k plus 1 into n, and so we're going to get something like this. So we're going to say k plus 1 I is equal to 0 for the sum I is equal to k times k plus 1 divided by 2, right? And so, what is this, or sorry, yes, this is right. So just looking at this, what can we say this is equivalent to? I mean, this is basically the sum of all digits leading up to k. But if we were to simply say the sum of all digits leading up to k plus 1, that would be the same thing as the sum of all digits leading up to k, but we would simply just add the digit that is k plus 1 like onto this, essentially. So what I'm going to do is I'm going to say this is equivalent to the sum of I is equal to 0, we have I here, plus k plus 1, and we're also going to show, and we actually should have written this up here, so let's ignore this for now. We're going to say, just over here, k plus 1, because that's what n is actually equal to, and then in this case it's going to be k plus 2, and that's going to be divisible by 2 in this case, right? Okay, so we have these two forms right here, and really what we want to do is make them look the same to prove that, taking that one extra step is really something that we can do, something that will allow our proposition to hold, right? So how can we do that? Well, one thing that we should typically do is whenever we find something that looks similar to our hypothesis, we should pretty much immediately, not necessarily immediately, it depends on the situation, but we should definitely think about substituting our induction hypothesis in. So basically what this is saying is, and I really should have written this out, that it holds for some k, right? So we know it holds for k, we're trying to show k plus 1, so we can write this equation out, substituting k in for n, right? Because we know k holds, by the hypothesis. So essentially what we're going to do is replace that with what it's equivalent to, which is k plus 1, divide that by 2, and then we're also going to have this plus k plus 1, and I'm just going to multiply this out. In this case we have k squared, 2k plus 1k is 3k plus 2 is that, so we're going to have out here we're going to have 1 over 2 k squared plus 3k plus 2. Okay, and let's see what we have. This is k squared plus k divided by 2. If we were to divide this side by 2, this would essentially be 2 here, and this would essentially be 2k. So then this would all be over the same. This would all be over the same denominator, and then in this case we can say 1 over 2. That's the k squared. We have a k plus a 2k, which gives us 3k, and then we have a 2 just over here. All right, and as we can see, these things are equivalent, so we have shown that k plus 1 does in fact hold. Right, and so that's sort of how we use induction to prove our propositions. I'm going to just kind of go over some of the other cases in the notes. So let me switch back over to the notes view, and I can't seem to find my mouse. Give me 1 second. Okay. All right, yeah, and so this is a bit of a better representation. Hopefully that's fairly clear right there. Okay. Now I'm going to move on to the second theorem, which is going to be theorem 3.2, and we are going to draw it out. Give me 1 second while I get things set up. Okay, so let's illustrate theorem 3.2. Switching over to Paint. This one, to me, is a little bit more straightforward. I just like it a little bit better. And essentially what it's saying is all numbers in the set of natural numbers, for all numbers in the set of natural numbers, that number inputted into this equation will be divisible by 3, right? So just sort of mechanically, we're going to go through this 3 steps in our process. And first one is going to be our base case. Again, we're just going to call this whole statement P again. So I'm going to say, given that our set is all of the natural numbers, we're going to input 0 first. So we want to check P of 0. And we're going to see, just 3 divide 0 minus 0. And 3, technically every natural number divides 0. So this is, I guess, trivially true. But it still checks out. So next we're going to move on to our inductive hypothesis, which is basically, as we've said before, we're just going to assume, we're going to make the statement that P of k, is true, given that k is greater than or equal to 0, given some arbitrary k in the set of natural numbers, right? And given that we know our k is true, we want to prove that our k plus 1 is also true, okay? It's going to be a lot of repetition at this point, but hopefully some different examples will help it sink in. So we want to say prove that P of k plus 1 holds. Okay, so let's see. Something that we can actually do with this is convert it. So if we remember, this is one way of representing something, but we can also say, if 3 divides n cubed minus n, then that means that n cubed minus n is equal to 3 times something, right? So we're going to use this fact, which is equivalent to what is above, in our inductive step, okay? So as we sort of did in the last problem, we're going to substitute in k plus 1 into the equation. So we're going to say, 3 divides, in this case it's going to be k plus 1 cubed minus k plus 1. So let's just do some algebra really quick. We're going to say, k cubed plus, and what would it be? I think it is 3k squared, and it would also be 3k squared and 3k, and then the ones will multiply each other, and then we also have this k plus 1, right? We're saying we're going to convert this into its alternate notation. We're going to say this is equal to some 3 times, I don't know, let's say d, for example. Okay, and something I'm going to do really quick is actually, within this step, I'm just going to distribute this negative sign right here. So I'm just going to, not the right one, I'm going to say negative k and minus 1. I'm going to say minus k and minus 1, right? Now, as we said in the last example, something that we really want to try to do is take whatever setup we have and, I guess, mold it into something that we've seen before. And usually that thing is the inductive hypothesis, right? So, given the terms we have right now, are you able to find something that looks like that? Well, once we distribute the negative sign, we can see that we have this term right here and this term right here. And we know that we can easily convert that into, something that is divisible by 3. So that's what I'm going to do. I'm going to take this off, just say it's 3q. Then I'm also going to take this off and this off, 1 minus 1. And all we are left with is this. And as we can clearly see, this expression right here is very much divisible by 3. And so we have effectively proven by induction that k plus 1 does in fact hold, and therefore all of the natural numbers satisfy this proposition. Okay? And again, I'm going to pull up my notes for this one, just so we can take a look at a cleaner version of it. Okay, and I'm going to pause here, and then we're going to set up the next equation, or next proposition. Okay, let's move on to theorem 3.3. So, essentially, what we're going to prove in this one, and I'm really just going to talk through this one a lot, not going to write a whole lot, is that given a map, and given that we can draw lines on it that will break the map up to 2 distinct parts, we propose that it is possible to color all segments using only 2 colors, such that colors that are the same do not overlap, do not share a border. And so colors that are diagonally across, that doesn't count, right? So, this red right here does not technically share a border with that red right there. As you can see, like, this is the border that the blue and the red share, right? And this is okay. It's fine for opposing colors to touch on a map, but we want the same colors that are used to not touch each other. So to prevent confusion, essentially, right? You can think of that as, like, using colors on a map to identify different countries. If there's 2 different countries but they're colored the same and they border each other, then you're going to think that they're the same country, so we want to prevent that, right? So, just starting off, as usual, we're going to perform our base case, and really what we're saying is, like, for n number of lines, n number of lines in the set of natural numbers, we'll be able to color our map using only 2 colors. So, if our map has no lines, then it's very obvious that we can color our map using 2 or less colors, because we only need 1 color to color it. Next, we're going to move on to our hypothesis, which essentially says, the same thing we've been saying. If it holds, we're going to say that this property holds for some arbitrary k, such that k is greater than or equal to our base case, and we're going to show that it holds for k plus 1. Okay, so, and k represents the number of lines that we've drawn on the map, right? So in this example right here, I'm going to say k is equal to 2, and this is sort of an intermediate step, but this is how the map should actually look like for k plus 1. K plus 1, which is equal to 3, right? Okay, and so with our inductive step in mind, we're going to try to verbally reason why this holds, right? So, there's 2 cases, kind of. We're actually going to look backwards in a sense. So, given k plus 1, it's possible that we could remove a line that was found earlier on in k, for example, like here. And, it's sort of trivial if we were to remove a line that, actually no. So say we were to remove this line right here, right? We know that that's just going to make us look exactly like k equals 2, the k equals 2 representation, and so in that case, it's pretty obvious that the colors should already line up, because our induction hypothesis says that p of k is true, right? But how can we be certain that, adding this line right here will allow us to make a map that is 2 colorable, right? So one property that we can notice is that once we're in our k equals 2 representation, and we draw this line right here, we essentially have these little pockets that kind of represent, what used to be there, right? So there used to be a blue in this area, a blue in this area, and a red in this area. But something we can notice by looking at k equals 2 is that if we are to color swap across a specific line, then we can, that's actually allowed, right? If we change the colors on one side of the line, then our property is maintained, essentially. So if that's what we do here, if we look at this line that we're adding and we swap the colors, so blue becomes red, red becomes blue, and blue becomes red, we can essentially show that all of the segments that have borders with other segments do not share colors with those bordering segments, right? And given that that's our only other case, we've shown just by being able to color swap like that we can in fact create a map with n number of lines that can be two colorable. So hopefully that makes sense. In my written explanation I probably do a better job, but really the reason why I'm illustrating these in the first place is for me to be able to recall what my thought process was when I understood or when I read through this. So I will enlarge it a little bit and I'll put it, I will not enlarge it that much. I mean, we know what the representation looks like, so let's just look at this right here. Maybe I can make it smaller so you can see. Okay, hopefully that's visible and legible. Yeah, so let's see. Yep. Okay, gonna pause for a bit so we can work out the next theorem. Okay, so we're actually moving on to another section, and this one is called Strengthening Induction Hypothesis. And this one I haven't actually really used in an actual practice problem yet, so I'm not directly seeing the utility of this, but for now we're just going to kind of mention it and do one example. So essentially what they mean is our first claim is that for all natural numbers greater than or equal to 1, the sum of the first n odd numbers is a perfect square. And basically we're able to get to a certain spot, but the way that we're saying, and let me just check this. When we get to the spot where we actually say that it's a perfect square, it's sort of difficult to see it's a perfect square of what exactly. I believe that's the place we get stuck at in the notes, but essentially the way that we overcome this is by making our hypothesis more specific to provide more structure, allowing us to actually come up with some sort of equation that we can work with. Because when we have these loose definitions of problems, it's harder to work on them. I think that's sort of the purpose of what this section is for. But essentially this is what we convert it to. We find that for all n greater than or equal to 1, the sum of the first n numbers is actually not just equal to some perfect square, it's equal to n squared. So we're going to show that really quick. Switch over to Paint. So I have the same theorem listed right there. And just to give a couple of examples, we're going to have on this side, let's see, n is equal to 1. We'll say, n is equal to 2, n is equal to 3, n is equal to 4, right? So first n odd numbers, so this is going to be odds, I'll say odd sum, and we could do that, do this, and I'll say n squared. Okay, so I'm going to just push that out there. 1 and 1, 1 plus 2, I'm sorry, first n odd numbers is what it is. That's 4. This is 1 plus 3 plus 5, which is equal to 9. and this is 1 plus 3 plus 5 plus 7, which in fact is equal to 16. So as usual, sort of going to verbally go through this. I might illustrate some of this. Base case, n is greater than or equal to 1, so why don't we plug 1 in? We see by this that summing all of the first 1 odd numbers in the set of natural numbers is equivalent to simply squaring 1. And looking at our induction hypothesis, we see that we're going to assume for some arbitrary k that's in that set of natural numbers greater than or equal to 1 that k holds, right? And now what we're going to want to do is prove that k plus 1 holds. Okay, so that's going to be our inductive step. And to illustrate how k plus 1 holds, we're going to sort of mathematically represent this. So give me 1 second. Okay, so the way that we can mathematically represent this, well, we have something that's evident for n squared, but how do we represent some of these odd numbers right here? I'm just going to notate that down here. So we're going to say the sum of the first n odd numbers starting at I equals 0. If we think about what's going on, really this is what's happening. 0, the very first odd number would be 1. Then we were to increment, now I is equal to 1. So our second odd number would be 2 times 1 plus 1, which is 3. So hopefully that makes sense. And what we were saying is that that is equal to n squared. And really what our inductive hypothesis was saying is, it really doesn't matter what value we use. So honestly, I'll keep it the same. But we're essentially saying that this holds for some arbitrary n that's greater than or equal to 1, right? And then we want to prove that k plus 1 holds. Or, we could even say n plus 1, but... So what are we going to do, right? So if we think about what this is, the sum of the first k numbers, or I guess the first n numbers, would be this, right? But the sum of n plus 1 numbers is simply this right here plus this plugged in, n plugged into there, right? So I'm going to say that is essentially, we're going to say that the k plus 1th number is equal to 2k plus 1, right? That's our k plus 1th odd number. Okay? And we can see that if we were to essentially plug in this value, 2k plus 1, into, give me 1 second, let me make sure I do this correctly. Okay, so let me formalize the inductive hypothesis a little bit more because I seem to get confused with that myself. So when we formulate the inductive hypothesis, usually the variable we are using in our equation is n, right? So the reason why we pick some arbitrary value k is to basically just say that that's some number that can be put into n's place, right? So we're going to say that assume p of k holds. And this is something I need to hammer myself. Assume p of k holds, and then we want to prove k plus 1 holds. Or we're going to say n is equal to k plus 1, right? So we have this right here, and if we imagine substituting k plus 1 in, as we saw in the very first proof, essentially all that is adding is maintaining this and then adding 2k plus 1, right? So, if this is actually equal to this, then we can say that really all it is adding 2k plus 1 to that, right? Hopefully that makes sense. Because, I feel like I've sort of already explained this, but, that logically follows. And just as we had substituted 2k plus 1 into that n right there, what happens when we substitute k plus 1 into this n right here, we get k plus 1 squared, which actually multiplies out to that. So I think I was definitely tripping up over my words there, but I hope it's clear now. I mean, let's look at the example to illustrate it a bit better. Right, so this is what we originally wrote. And yeah, I'm going to skip the other theorem in this section, and we're going to move on to the next section. Let me see. So actually, yeah, so I'm going to skip 3.5, but let's see. Oh, I think something is missing here. Yeah, simple induction versus strong induction. Okay, so basically everything we've been doing now has been considered simple induction, right? And now we're going to introduce something called strong induction, and I will quickly illustrate what the difference between the two is. So the main difference is in the inductive step. For simple induction, we're assuming that P of k holds, and so what we're saying is that we're trying to prove P of k plus 1 holds, right? Given that the value right before us holds, we want to show that the one right after also holds, okay? But in strong induction, what we are saying is that given that we have some value, we'll call it n, and given that all of the values before n hold with our proposition, then we are going to try to show that n plus 1 also holds. And let's look at the definition. Yeah, it's pretty much the same, and I guess the domino effect is sort of what they were compared to. And I'm going to look at theorem 3.6 really quick. And let's see, maybe it'll just be more beneficial if I just talk through it. So the example they give is for every natural number n greater than or equal to 12, it holds that n is equal to 4 times some x that's a natural number and 5 times some y that's a natural number. Okay? And what we are essentially going to try to prove is that for some value greater than 16, greater than or equal to 16, that n is equal to 4x plus 5y holds, right? And so just at a high level, if we were to use simple induction and we were to say that we want to show that some n that's greater than or so basically k is going to be greater than or equal to 15, right? This is going to be our inductive hypothesis we can see right here. So our k plus 1 is going to be greater than or equal to 16, right? But unless we have strictly proven that k holds, then we cannot really prove that k plus 1 holds, right? And the only way that we will have been able to do that, given our initial proposition, is to prove that all the values from 12 leading up to 15, up to and including 15, that all of them hold, right? So hopefully that makes sense. Simple induction, k is true, so k plus 1 must be true. Strong induction, k is true and all values before k, like leading up to k, are true. So then k plus 1 must be true, right? So essentially the cases in which you would want to use strong induction are when you have some value and you want to prove the plus 1 of it, but it requires you to look at smaller components that are less than your n. I guess arbitrarily that doesn't make a whole lot of sense, but when we look at an example, maybe after this, it'll hopefully make more sense. But yeah, I mean, essentially these are our base cases right here because we're proposing that n is greater than or equal to 12 for this equation, and so we're sort of building up to 15 because our actual hypothesis is stating that k greater than or equal to 15 can be represented as this equation. And because we have shown that, because we have bridged the gap between our initial proposition and our induction hypothesis, then we can make our inductive step and show that k plus 1 holds, right? And so just using some simple algebra, we can subtract out 4 and see that k plus 1 can be represented by 4 times some quantity and 5 times some quantity. So hopefully that makes sense. I'm going to move on to the next proof. Why would this proof fail if we use simple induction? So yeah, we sort of explained that. We can read this if we want. I'm going to look at theorem 3.7 at this point, and let's just see what it is. So it's saying every natural number n greater than 1 can be written as a product of one or more primes. Okay, so base case is 2. We're just inputting it into the above hypothesis, and we know 2 is true because 2 is a prime number. And then for our inductive, we put it into our proposition. Now we're going to formulate our inductive hypothesis, which is going to say that we're going to assume that there's some k that is in between our base case of 2 and the n value, right? The n value. We're going to assume that all of those are true. And really what this is saying is that any k in between is true, right? So now we're going to want to say that k plus 1 is true. Okay, so how should we do that? Well, we have our two cases down here. If it's the case that n is prime, then we know that it's the product of at least one prime and something else, because for example, if the prime is 7, we can just do 7 times 1, and that is obviously a prime. However, if it's not a prime, then we will kind of look at the two values that are used to get our number. So I will illustrate the example from the notes. So imagine we have 42, right? And we see that 42 is equal to two numbers, and the two numbers we're going to pick are 6 and 7. 7 is trivially prime, as we said before, but when we look at 6, we don't immediately see it as prime, right? But if we take this 6 and sort of input it into our induction hypothesis, which we in fact are able to do because our k plus 1 is 42 and 6 is within that range, it's less than 42 and greater than 2, then we can see that 6 is actually made up of 2 and 3. And 2 and 3 are both prime numbers. So because 6 is made up of 2 and 3, which are prime numbers, and because 7 is a prime number, we can safely say that that natural number 42 can be written as a product of, in this case, more than just one prime number. And we can similarly break every natural number into this sort of multiplication by using that logic. So essentially, that's what we do. We're going to say n is equal to x and y, and then we're going to look at x and y and plug it back into our proposition and see that both of those are true, so it must be true that p of n is in fact made up of prime numbers as well. Okay, so hopefully that makes sense. Really quick, why would the proof fail if it used simple induction? And that sort of goes back to what we were saying. Simple induction would say, if 41 is true, then, or I guess if p of 41 is true, then p of 42 must be true, right? But if we try to use the same approach, where we say 42 is equal to 6 times 7, well, we might be able to figure out that 7 is a prime, but we have no way of knowing if 6 holds for our proposition that it is a product of one or more primes, right? And that's because we never said in our induction hypothesis or in our assumption that that is the case. All that we said is that 41, when inputted into our proposition, holds. So that's why we need to use strong induction, which simply says from our starting value all the way up to the value we're looking at, which is n, all those values hold. So hopefully that makes sense. And now we're going to move on to the next section, which is recursion, programming, and induction. And really quickly, I'm going to go over these. I kind of whizzed through the example in the notes because I was already familiar with Fibonacci. And essentially what Fibonacci, it's a sequence of numbers. What it is you start off with 0 and 1. Those are sort of like your base cases. Every number after 0 and 1 is calculated by summing the two previous numbers. So for example, we start out with 0 and 1. If we want to move on to the next number, we're going to take 0 and 1, sum them up to get our next number, which is 2. Then if we want to get the next number, we're going to take 2 and 1 and sum them up to get 3. Hopefully that makes sense. And they sort of said that this is how we would do this using programming. We can do it recursively, and I will very briefly illustrate what this looks like. Open a new. So the easiest way to visualize this is by using a tree diagram. So let's say that we're trying to find the fourth Fibonacci sequence number, right? So looking at our equation, and did I switch over? Yeah, I switched over. Looking at our recursive equation, essentially all we do is if we don't hit our base case of 1 or 0, then we're going to call the function on n minus 1 and n minus 2. Okay? And we're going to sum up those two numbers, right? Because the n minus 1th number is the number directly behind it. The n minus 2th number is the number that is directly behind that n minus 1th number. And those are the two numbers we want to sum together to get our nth number. So just visually, let's say we want to find what that is. Well, so because we're not at a base case of 0 or 1, we're going to say n minus 1 down this way. We're going to say n minus 2 down this way. And then we're going to say n minus 1, n minus 2. We'll say n minus 1, n minus 2, n minus 1, n minus 2. Okay? And, we sum these up to get that value, we sum these up to get that value, and so on. And that eventually gets added up here. But something that they tried to point out was that if we use this implementation, we're going to run into a lot of duplicated work. And as we can see, there are multiple ways to get from 4 to 2. Right? We can subtract 2, or we can subtract 1 twice. And because of that, we will end up computing what Fibonacci of 2 is 2 times in this case. But if you imagine a number that's really big, like let's just say it doesn't have to be that big. Let's say it's 50, right? There are several ways to get from 50 down to, 2. Right? And so we will be calling this exact same process several times. And so something that this actually comes up a lot in programming interviews, something we would want to do to overcome that is to create a cache of any Fibonacci values that we have seen before. So as soon as we see it again when we're recursing down, we don't have to go all the way down, this tree right here. We can simply just stop here, get its value, and then float back up the recursive stack. Okay, and actually a nice iterative solution that they gave was, we literally do the code equivalent of the problem description, which is, if we have our base cases, then we set them equal to 0 or 1. Otherwise, all we're going to do is add 0 and 1, add kind of like the numbers next to each other, up until we get to that nth number that we're looking for, right? So hopefully that makes sense. Yeah, so binary search, I honestly didn't feel like this one was very worth in terms of actually proving. So I guess I can talk about the explanation really quick. The metaphor they gave in the notes is actually a pretty good one. So say you're looking for a word. Let's say the word is taco. Typically, or one way that you would do this is to open the dictionary in the very middle, and whatever letter, or I guess letter section you end on, you're going to say, well, okay, is taco, further back in the dictionary, or is it further forward in the dictionary? And based on that, you're probably going to say, well, taco is probably to the right of whatever letter it is. Say we land at M. And so we're going to take the back half of the dictionary and then split that, and then see what letter we end up at that point. And essentially, the base case for this is, upon splitting as much as we can, and upon getting to the point where our word is neither less than or greater than the value that we're looking at, then it must be the case that we've either found the value or that the value just doesn't exist in the dictionary. And so the proof was pretty arbitrary, or I guess it was arbitrary, but it was like trivial is really what I would classify it as. Because it was saying, like, our base case is if we're on one page and like we have one word, the base case is either that the word is there or that it's not. And then the proof was just like, okay, assume we have more pages, and then we basically apply we applied the binary search technique, which is to, look at the upper half or the lower half, depending on which side of the middle our letter falls on. And then we know that it will work simply because we have the base cases to catch it. That's pretty much what it says. So it feels like just sort of unnecessary to go through all that work to formally prove it. But yeah. I'm going to move on to the next section, which is false proofs. And yeah, this one was sort of interesting. I think what it's trying to illustrate is that if we claim something that's just incorrect, we might be able to come up with some sort of proof. But if it's blatantly incorrect, then there should pretty much always be some sort of counter example to it. So, I don't know. This section seems kind of unnecessary, but I guess it was sort of interesting, the proof that they gave. And what that was is that all horses are the same color, right? And I'm sort of visually going to explain this one again. So they said that they're going to use induction, right? I think they use simple induction. So, if we have a set of horses and there's only one horse in that set, then all horses in that set are the same color, right? That one horse is that one color. Now we're going to say, for some arbitrary number greater than or equal to a set of just one horses, we're going to say a set of, let's say, k horses, this holds, right? So we're going to say, prove that this holds for k plus 1 horses, right? So we're going to have a set of k plus 1 horses, and we're going to say, okay, we're going to look at the first k horses in the set, right? And we know by our inductive hypothesis that a set of k horses have all of the same color, right? Okay, but our set is k plus 1, right? So this time we're going to look at I guess we're going to shift that k set over by 1. So instead of looking at the first at 1 through k, we're going to look at items 2 through k plus 1, right? And because the number of items in that set is equal to k, the inductive hypothesis tells us that p of k holds, right? So if the set of elements from 1 to k holds and the set of elements from 2 to k plus 1 holds, then it must be the case that all of the elements in that set have that same color. But one counterexample that is pretty clear is that if we have a set of 2 horses and we look at the first half, we're going to see, okay, we know that it must have like one type of color, right? Because our inductive hypothesis, because our k plus 1 value is 2, and our k value is 1, we know that a set with one horse, by both our base case and our inductive hypothesis, we know that a set of one horse tells us that they all have the same color. Okay, so we're looking at element at index 0. That has one horse, so it must have one color. We're going to look at element at index 1. That has another horse of one color, but because they share no sets, if that makes sense, like the first element, if that's its own set, and the second element, if that's its own set, like they don't share anything, obviously. So when we look at the whole set and we try to say that they both have the same color, well, that's not necessarily true, right? Because in the previous example, there was some middle that both the first element and the last element shared. But in this case, because they share no middle, then it's not necessarily true that the first horse and the second horse will have the same color. Right, so that pretty much wraps up induction. Yeah, I think I got a better understanding of it myself. Some things that I just need to keep straight in my head are that for simple induction, we're assuming that k holds, so we want to show that k plus 1 holds, right? And all that we can rely on is that k holds, right? But for strong induction, we can say that given that there's some value that goes from, our initial value all the way up to n, we know that any of those values in there hold. And so we want to show that k plus 1 also holds. And we can rely on the fact that all of those previous values also holds in our strong induction proof. So hopefully that makes sense, and that about wraps up note 3.